every type of planetary defense strategy. Space is complicated. We make it simple. Nothing in the solar system has signed a peace treaty with Earth. Every year, thousands of new asteroids are cataloged, and every single one of them is technically a candidate for a future collision, however unlikely. The good news is that this is one cosmic threat humanity has actually started building real tested solutions for, not just theories on a chalkboard. We're going in order from the simplest, cheapest strategy to the most extreme, least tested one, then we'll sort them a second way by how much warning time each strategy actually needs. Because on this list, the right answer depends entirely on how much time you have left before impact. Do nothing and evacuate. We begin with the strategy nobody wants to hear, and also the only one that requires zero new technology at all. If an incoming object is detected too late, too small to justify a deflection mission, or simply too difficult to redirect in the available time, the only remaining option is identifying the predicted impact zone as precisely as possible and evacuating it. Here's the fact that should genuinely bother you. This isn't a hypothetical fallback. It has already happened for real, on a smaller scale. In 2013, a meteor roughly 20 meters across entered the atmosphere over Chelyabinsk, Russia, completely undetected in advance, exploding with the force of several hundred kilotons of TNT and injuring over 1,000 people, mostly from shattered glass, with zero warning time available to evacuate anyone. Here's the part that lingers. Objects in this size range are common enough and currently hard enough to detect in advance that evacuate and hope the object airbursts rather than reaching the ground intact remains right now the actual practical plan for a meaningful category of potential impacts, not a last resort reserved for the most extreme scenarios. The gravity tractor. Here's the twist. The gentlest, slowest deflection method on this list doesn't touch the asteroid at all. A gravity tractor is a proposed spacecraft that would fly alongside a threatening asteroid for months or years, using nothing but its own small gravitational pull to very gradually tug the asteroid's path off its collision course, exploiting the same basic physics that keeps a moon in orbit around a planet. Here's the fact that should genuinely bother you. The force involved is almost unimaginably small, but because gravity acts continuously and predictably, even a tiny, patient tug sustained over years can add up to a meaningful change in trajectory without ever needing to touch, drill into, or understand the asteroid's internal structure at all. Here's the part that lingers. This makes the gravity tractor uniquely valuable for one specific reason. Because it never physically contacts the asteroid, it works identically well, regardless of whether the target is solid rock or a loosely bound rubble pile, sidestepping one of the biggest uncertainties that complicates every other deflection method on this list, at the cost of requiring the single longest lead time of any strategy here. Kinetic impactors. Here's the reframe. This is the only deflection method that has actually been tested for real against a real asteroid, and it worked. A kinetic impactor deflects an asteroid the blunt way, deliberately crashing a fast-moving spacecraft directly into it, transferring momentum on impact to nudge its orbital path, the same basic physics as a cue ball hitting a billiard ball. In September 2022, NASA's DART mission did exactly this, deliberately slamming a spacecraft into a small asteroid moonlet called Dimorphos, successfully shortening its orbital period around its larger companion asteroid by over half an hour, dramatically more than mission planners had conservatively predicted. Here's the fact that should genuinely bother you. The deflection was significantly amplified beyond the impact alone by an effect called momentum enhancement, where debris ejected from the impact crater itself acted like a secondary rocket thrust, meaning the asteroid's internal composition, something we can't always know in advance, directly determined how effective the same impact actually turned out to be. Here's the part that lingers. DART worked on a moonlet roughly the size of a large building, at a target chosen specifically because it posed no actual threat to Earth. Scaling this exact strategy up to a much larger, genuinely dangerous asteroid remains untested at that scale, and would still require years of advance warning to be useful at all. Nuclear deflection and disruption. Here's the fact that reframes this entry as both the most powerful and the most controversial option on the list. For the largest asteroids, or for situations with dangerously little advance warning, a nuclear device could theoretically be detonated near, rather than on, an asteroid's surface, vaporizing a thin outer layer that then acts as a powerful one sided thrust, pushing the asteroid off course without physically shattering it. Here's the fact that should genuinely bother you. This method is generally considered more effective, pound for pound, than any other deflection strategy on this list, particularly for very large objects or scenarios with only months of warning rather than years, precisely because nuclear detonation releases vastly more usable energy than any other approach humanity currently has available. Here's the part that lingers. Using this option in a true disruption scenario, actually shattering the asteroid rather than gently deflecting it, carries a genuine risk of turning one large, trackable threat into multiple smaller, less predictable fragments, some of which could still strike Earth, meaning even the most powerful tool on this list comes with a real chance of making a bad situation only partially better rather than fully solving it. Ion beam shepherding and laser ablation. Here's the fact that closes the gap between the gravity tractor's extreme gentleness and the kinetic impactor's blunt force. An ion beam shepherd would station a spacecraft near an asteroid and fire a continuous stream of charged particles directly at its surface, gradually eroding material and using the resulting recoil plus a counterthrust from the spacecraft itself to slowly push the asteroid off course over an extended period without ever physically touching it. A closely related concept, laser ablation, proposes using a powerful focused beam of light instead of a particle stream, vaporizing surface material to produce a similar continuous low thrust nudge. Here's the fact that should genuinely bother you. Both of these methods remain almost entirely theoretical, tested only in extremely limited laboratory conditions rather than on any real asteroid, and both share a specific vulnerability that DART's kinetic impact didn't. They require the spacecraft to remain precisely positioned and continuously operational for months or years, meaning a single mechanical failure partway through the deflection campaign could leave the mission incomplete with far less time remaining to try something else. Detection and early warning systems. Here's the fact that reframes every strategy above as functionally useless without this one. No deflection method on this list works without enough advance warning to actually execute it, and detection remains the single biggest bottleneck in planetary defense today. Ground-based and space-based survey telescopes continuously scan the sky for near-Earth objects, and while astronomers have identified the overwhelming majority of the largest, most civilization-threatening asteroids, the population of smaller objects, still large enough to devastate a city, remains significantly less thoroughly catalogued. Here's the fact that should genuinely bother you. An asteroid similar in size to the one that caused the 1908 Tunguska event, discussed elsewhere on this channel, could plausibly go completely undetected until days or even hours before a potential impact, given current survey coverage gaps, particularly for objects approaching from the direction of the sun, where ground-based telescopes are effectively blind. Here's the part that lingers. Every dollar spent on improved detection capability directly extends the available warning time for every other strategy on this list, meaning the least dramatic, least headline-grabbing category here may quietly be the single most important one. A gravity tractor or kinetic impactor is worthless if nobody sees the threat coming early enough to launch it. Civil defense and infrastructure hardening. Here's the fact that closes this list by shifting focus away from the asteroid entirely toward preparing the ground it might hit. For smaller objects too minor to justify a dedicated space mission, but still capable of significant local damage, planetary defense increasingly includes coordinated emergency response planning, impact probability modeling, evacuation logistics, and structural guidance for withstanding an airburst shockwave, treating a potential small object impact more like a hurricane or earthquake than a deep space engineering problem. Here's the fact that should genuinely bother you. This category is the only one on the list that doesn't require detecting the object years in advance to be useful at all. since even a warning of just a few hours can meaningfully reduce casualties through evacuation or shelter guidance. The same lesson learned directly from the injuries caused by the 2013 Chelyabinsk event. Here's the part that lingers. Unlike every space-based strategy discussed above, this approach doesn't stop an impact from happening at all. It simply changes what happens to the people standing underneath it. A distinctly unglamorous, entirely earthbound half of planetary defense that gets a fraction of the funding and attention of the space missions, despite currently being the only strategy actually available for the shortest warning scenarios. International coordination and tracking networks. Here's the fact that closes out the strategies with the least glamorous, most bureaucratic entry on the entire list, and also one of the most quietly essential. Planetary defense isn't run by a single country or a single agency. It depends on a coordinated international network, including bodies like the International Asteroid Warning Network and sharing detection data, confirming potential threats independently, and establishing agreed upon protocols for exactly who has the authority to decide when and how a deflection mission should actually be launched. Here's the fact that should genuinely bother you. No binding international treaty currently exists that clearly resolves who would have final authority to approve a real deflection mission, including a potential nuclear option in a genuine emergency, meaning a real time-critical threat could plausibly run into diplomatic and legal uncertainty at the exact moment speed matters most. Here's the part that lingers. Several planetary defense exercises have been conducted specifically to simulate this exact bureaucratic bottleneck, deliberately testing how quickly international coordination could actually happen under realistic time pressure. And the results have repeatedly highlighted communication and authority gaps that no amount of clever spacecraft engineering can solve on its own. Let's sort these 8 again, a different way, not by how they work, but by how much warning time each strategy actually needs. On the decades of warning end, the gravity tractor and ion beam shepherding, both requiring years of sustained, continuous operation to produce a meaningful course change. On the years of warning end, kinetic impactors proven effective by DART, but still requiring enough lead time for the resulting small trajectory shift to compound into a meaningful missed distance by the time of the original predicted impact. On the months of warning end, nuclear deflection, the most powerful single option, reserved for scenarios too urgent or too large scale for the gentler methods to work in time. On the hours to days of warning end, civil defense and evacuation, the only strategy that can still meaningfully help when almost no advance notice exists at all. And underlying every single one of these, detection and early warning systems, the category that determines which of the other options are even still on the table by the time a threat is actually confirmed. It's worth remembering before we close that DART's 2022 test wasn't just an engineering demonstration. It was the first time in recorded history that humanity deliberately, measurably changed the motion of another celestial body on purpose. Every previous entry in human history involving a change to an object's orbit was either a natural event or an accident. Here's the fact that should genuinely bother you. The target chosen for that first deliberate test posed zero actual threat to Earth, meaning humanity's very first successful planetary defense test was, by design, a practice run rather than a real emergency response. The actual first real-world use of any of these strategies against a genuine threat hasn't happened yet, and nobody knows exactly how smoothly the transition from successful tests to real deflection under pressure will actually go. Here's the last thing worth sitting with. Every strategy on this list, from the gentlest gravitational tug to a nuclear detonation in deep space, is completely useless without one specific piece of the equation, seeing the threat early enough to act. The dinosaurs didn't have a choice in the matter. We are the first species in Earth's 4.5 billion year history that gets to actually try. Not bad for stick figures on a rock.